Hello, good morning, welcome to Connect. Kugan today will be talking about an optimization that he is working on at the Linaro toolchain working group. This is redundant zero and sign extension elimination, which is a very useful optimization for ARM and ARC64 targets.
Thank you, Maxim. So in this presentation, I'm going to be talking about the work we are doing with respect to zero sign extension elimination in GCC. So here, basically, I'm trying to cover what is listed here. So I'll start off with the basics and talk about what is zero sign extension elimination and why do we need that. Then I'll go into how GCC minimizes redundant zero sign extensions and its shortcomings. With that one, I'll go into two new techniques we are trying to propose here, namely using value ranges to remove redundant extensions and a separate tree-level pass that can do register promotion so that we can minimize redundant extensions. With that, I will conclude this presentation. Due to, I have to cover a lot of material in this presentation, so I'll have to skip some details. So if you feel that something is not clear or if you have any question, feel free to stop me at that point. Okay, let's look at what is a zero sign extension operation is. So if a value in a register is unsigned, and if you're going to convert that into a wider mode, we have to do zero extend. For example, if you look at the picture shown here, and we have an 8-bit value, F0H, and if you're going to zero extend, assuming that it's an unsigned value, we are going to add zeros when you add, zero extend it. So we are going to add zeros to the missing bits. Similarly, if the value in the register is signed, and if you're going to convert that one into a wider mode, we have to replicate the signed bits to the missing bits. In this particular example, the signed bit is 1, so we will be adding ones. Had the signed bit been 0 for this value, say if it is 70 hexadecimal value, then we would have added zeros to the missing bit, which effectively produces the same results as zero extend. So you might want to keep that one in mind because we are going to use this in one of the optimization. In ARM and ARC64, we have this explicit extend instructions for extending zero and sign extending byte and half word. And also, in some of the instructions, we can actually zero sign extend one of the operand in ARC64. This might not necessarily be going to speed up your operation, but at least it can reduce space. And it can have some secondary benefits, like improved cache utilizations and improved register pressure, because we don't have to do a copy.
So I have a question.
Yes, Maxim.
Do all instructions in ARC32 and ARC64 can do automatic sign and have unsigned and signed versions, or only few of them have both unsigned and signed versions?
We have for 8-byte, byte and half word. Yeah, we do for in ARM and ARC64, if that's your question.
Okay.
Yeah.
So the question I was thinking is that some architectures have instruction versions, which are half of the instructions are signed, and they have same instructions which do essentially the same thing, just on the unsigned types. And in ARM and ARC64, we have just specific instructions which are signed to promote, to do the promotion, but the rest of the instructions operate regardless of the signedness of the data type.
Yes.
Except multiply and divide.
Yes. Yeah. Operations. Yeah. Yes, that's right. Yeah. And also some of the other instructions also can do explicit or no implicit extensions, like when you do a load register byte or load register half word, it essentially loads a byte and extends it to the native type. Okay, now that we have looked at what is a zero sign extension operation is, let's look at why do we need that one. One of the first places where we usually see a zero sign extension is due to ABA compatibility. That is, ABA dictates what can be there in a register beyond the type width when you pass an argument and when you return a value from a function. And in AAPCS 32, it states that all the argument register and return value registers have to be properly zero and sign extended. And in AAPCS 64, they can have unspecified values. So let's look at a simple example here. So we have a function foo which takes two arguments, val1 and val2, and return a character here. And in ARM and AX64, these arguments value1 and value2 are going to be passed in register 0 and register 1, and the return value will come out in register 0. So keeping that one in mind, if you compile this program for AX32, the ABA says that the arguments will be properly extended by the function which calls foo. Sorry, the function which calls foo. So we can go and straight away add that one. But once we add, we have to make sure that the value is truncated for the type and extended. So we need that extension instruction here. Similarly, in AX64, we don't have such guarantee because like the arguments can have undefined values beyond the type width. So we have to do the extensions before we add. So here you can see that it's being extended before adding, but we don't have to do anything with the result because ABS says that we can leave undefined values. That's one of the reasons why C extension. But the main reason why we need extension, zero or sign extension, is for type conversions. So let's look at a couple of simple examples here.
These two examples do the same thing?
Sorry.
These two previous examples do the
No,
same thing?
yes. I mean, which one? I mean, this one.
Two examples are-
Oh, no, these are, okay. The first one is the C code. The second one is the code generated for AX32. The first, and the third one is the code generated for AX64.
They're not doing the same thing.
They are doing the same thing.
So
They are just adding.
the first example is truncating after the first.
Yeah,
and the second
because
one-
the ABS says that you have to do.
That's the rules of the API.
Really?
Yeah.
I think you can read the comments above. Okay, so let's look at the type conversion. And here I have a function foo which takes an integer and returns a char value. And if you compile this one for AX32, we have to, I mean, due to the ABI, like, though this is going to be a type conversion example, but due to the ABI requirements, extensions are going to happen in different places, like whether it's on the caller or callee. So for example, for this foo, when you compile this one for AX32, we have to properly extend before we can return, so we have to do the extension here. But in case of AX64, we can pass the undefined value, and the function which calls foo has to do the extensions there. Similarly, if you have a function bar which takes a character and return an integer, we know that according to the ABI, it would have been properly extended for AX32, so we don't have to do anything, just return the value. But for AX64, we don't have that guarantee, so we have to do the extensions here, because like we are going to return a 4-byte value, so it's our duty to extend it here. Okay, now let's go into GCC and see what GCC does and how GCC generated these extensions. Typically, in GCC, you see Subbridge and extensions are generated while converting from tree to RTL for number one, type conversions, and number two, for computations in promote modes. And some of these extensions are or may be redundant, and subsequent parsers in the GCC tries to optimize them. Example, combine and redundant extension elimination pass can combine the extension with its use to simplify instructions. And I'm going to show you these two examples in the subsequent slides. And also, there is this RTX simplification routines spread throughout the RTL. They work based on the attributes set by the tree to the Subbridge promoted mode. So basically, like when you have a Subbridge, you can from the tree level, based on the type, the tree sets SRP signed or SRP unsigned attributes to say whether that Subbridge is already promoted for the type. Is that being?
So just a small announcement. At this point, we are getting into GCC compiler internals. So if you have questions about the terms that are being used, ask, and we will try to explain in greater detail.
What's a subbridge?
Okay, Subbridge is basically like you have a register, and part of the register is Subbridge. So basically, like you have a 32-bit register, and you have an 8-bit value in that one. So that 8-bit part is Subbridge.
Subregister. So it's an operator on a register to.
Yeah, it's a notion used in GCC internal representation RTL. So that yeah.
It is a way to address specific bits in a register. So instead of addressing the whole register, you address specific bits in that register.
Yeah, I think the SRP sign or SRP unsigned are regulars, right?
Sorry?
Red nodes. Register nodes.
No, it's actually an attribute for the Subbridge. Like when you have a Subbridge, and when the Subbridge is promoted to a wider mode, you set this attribute. Yeah. So which says basically SRP sign means that value is already zero extended for sign extended in the wider mode. So you don't have to do that one if you need to do sign extensions. But if you do need to do unsigned extension,
It's a paradox.
sorry.
I mean that if you Subbridge narrow mode to wide mode, then it means paradox Subbridge.
I'm not talking about paradoxical subregister here. I'm just talking
So
about normal.
it's the signed and unsigned SRP is attribute.
Attribute for a
Yeah.
Subbridge which
So
is promoted.
Another question is that the promote mode is a tree expansion. When you do the type checking, you get the expression for the type, so you will do the promote mode.
No, not really. Promote mode is actually like the backend specify.
Yeah, you specify the backend to promote mode. So when the tree expansion, you get the expression for the type. The type for the expression, you will do the promote
Basically,
mode.
like if you have a addition in character, so if you have an x plus 1, the promote mode says that you have to do this operation.
So only there is the store to the memory, there will be the narrow or the Subbridge will generated. Otherwise, the computing will based on the machine world.
Yes,
Right?
Yeah, that's exactly why you have this promote mode.
Yeah.
Yeah.
So
basic-
why this is
I
qualified
think,
API.
I think I can clarify your questions in one of the subsequent slides. I mean, I have an example in the subsequent slide. I can probably.
Yeah. So please go on. So
Yeah, I
okay.
can come back to that one. But basically, what this attribute says is that when you have a Subbridge, and if it's promoted means that it's being used in a wider mode. SRP sign means it's already.
I mean that the computation is also based on the machine world. So
Of
always promote.
Of course.
Yes.
Yes. So what's the question there?
I think that the promote mode is not a pass during a.
Oh, no, I'm not saying promote mode is a pass here.
It's doing on the tree.
Promote mode is
Right.
used in tree, used in RTL. It's used everywhere. It's a target defined macro.
Yeah.
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 So which says that operations has to be done in this mode.
Yeah.
So yeah, GCC uses it everywhere.
Yes.
Yes, that's not a pass. I'm not saying that it's not a pass. Yeah. Okay. So basically, this RTX simplifications routine can use these attributes to optimize. Oh, sure.
Okay. Is the SRP sign or SRP unsigned available in GCC 4.9?
Yes,
Okay.
it is.
Yeah. You don't see this
Yeah.
reverse GCC.
It should be there for a long time, I think.
When is the two attributes introduced in GCC?
I'm not entirely sure, but I think it should have been there for a long time.
Okay.
Yeah. Yeah.
Okay. Thank you.
So let's look at a combine example. I mean, as I said earlier, combine combines the extension with use if the target has support for that one. For example, if you look at instruction 3 and instruction 8 here, we have an extension followed by a use. And combine will try to combine these two instructions together if there is a support for such instruction in the target, basically the machine descriptor. So in this case, AArch64 does have support for such instruction, and it can optimize it. Please note that combine as such is not meant for Zerosign specific things, but it helps here. And also, combine works only within a single basic block.
What is combine?
It's a pass in RTL pass, which basically, as the name suggests, tries to compile multiple instructions into simplified instructions based on a cost model.
Yeah. So it takes two instructions and combines them into one, or takes three instructions, combine them into two, or sometimes four instructions, combines them into three.
Yeah, something like that. So another optimization pass which is useful for redundant extension is redundant extension elimination pass, enabled for AArch64. This pass actually moves extensions to definition of extension source. So if you look at the example here, we have an extension at instruction 19, and the extraction source is actually defined in instruction 11. And it will try to move the instruction 19 to 11 and try to combine that if, of course, the machine supports such instruction. 1, 2, it's legal to do that one. So, and in this particular case, the AArch64 has such instruction, and also it's legal, so it can do this optimization. And this particular optimization pass can move instruction across basic block because it works based on data flow information. And other thing is it runs after the register allocation is done, so it doesn't really help in register pressure from that perspective. And also, it's not going to be able to use extension followed by use, as might be the case when ABI mandated extensions in the top. Now that we looked at how GCC generates extensions and limitations to some extent with combine and the redundant extension elimination pass. And also, we also looked at what the RTX simplification routines can do. And I understand that there are still some questions for that one, and I'll come back to that one in the subsequent slides. And part of the reason why it's pretty hard to remove extensions in the RTL level is that signed information is actually lost when you are in RTL. And only information you have when you optimize is the SRP signed and SRP unsigned attributes. So what can we do to improve this one? Number one, we can provide additional information to RTL from tree. Number two, change the tree such that extensions are minimized while converting to RTL. So we are going to look at these two approaches next. Yes.
So I think that you provide two approaches are based on the generic architecture. It's architecture free or centrally. It's not specific to AX64.
Yes, that's true.
Okay.
The first approach is based on using the value range to remove redundant extensions. So what is value range? In tree level, there is a value range propagation pass which can compute value ranges for SSA names when it's possible. And if meaningful value ranges can be computed for SSAs, it will provide with value ranges like 3 to 10. And if it can't, then it will say that it can't. And using this information, we are adding another attribute to SRP signed and SRP unsigned. We are also adding another attribute called SRP signed and unsigned when the value is actually extended for signed and unsigned. Basically, the signed bit for that value is 0. Yes.
So first a comment, then a question.
Yes.
In GC, there are several layers of intermediate representation. We have at the top tree level, which has rich information about data types. And then we have RTL level, which is register transfer language, where we have significantly less information about data types. What parts of your optimization are working at the tree level, and what part? And is there a part at the RTL level?
Yeah, I mean, in tree level, we are not doing any optimization as such. We are just propagating the information value range propagation pass generated to the SSA name. So when you look at any SSA in the tree level, you have that attribute stored as a range info, and we use that information in RTL expansion. So when we move from tree to RTL, we use this information and add this attribute.
Why that information was not already there at the RTL level?
The problem was most of the VRP-based optimization happens within the VRP pass itself. Value range propagation pass itself. So nobody actually needed it. But now that we have propagated, I know that some others are using it. Some other passes are using it. So, for example, you have a statement like a conversion statement here in the tree level. And we know that based on the value range information that the value 6 is going to have, always going to have, the variable 6 is going to always have value between 3 and 10. So that means that we can say that the value in this register is already 0 and sign extended. Because it's a half integer conversion. So, and with this information, we can actually change some of these RTX simplification subroutines such that they can remove additional extensions. So I'm going to show an example here.
So how does the fact that the value between 3 and 10 gives us the fact that it is already sign and 0 extension?
Okay.
Either that sign and 0 extensions will be a no-ops, or that they are already done?
They are already done, basically. The thing is, here, all the registers are having their values in promoted modes. And so in case of ARM, the promoted mode is ARM in AX64. The promoted mode is SI mode, so 4 byte. So we have a value in 4 byte, and that value is going to always be between 3 and 10. So if you take that value, subtrage half integer and extend, you are not doing anything because it's already done. And similarly, if you take that value, subtrage half integer and sign extend, it's also going to be the same thing, 0 and sign extend. So the value is already 0 and sign extended, and it's a no-op. So that information we are actually propagating.
So I guess your solution is that you propagate the value range into RTL, then you add a pass to optimize some of the Subbridge and sign extension. Is that correct?
We don't really propagate the value range to RTL. We just propagate the value range to all the SSA variables and use that SSA information while we expand to RTL.
You do this at the expanded phase.
Expansion, exactly, yeah.
Okay.
So yeah, so during the time of expansion, these attributes are set for the RTL subbridge. So,
but VRP to expand this, it still passes, so you still to carry the info between?
Yeah, VRP gathers that information and sets that information in VRP to the tree SSA.
Yeah.
Tree SSA actually has that value till expansion. And
okay, see.
Okay.
Thank you.
So let's look at another simple example. Here, based on this value range information, we can actually remove these two sign extensions. And I'm going to show how we do this one in the subsequent slide. So here, the value range propagation pass is going to gather value ranges for all the variables here. I'm not showing everything here because obviously I'm limited for space, but if you compile this program in GCC with fdump tree all, you can actually see that one, and some of them are not going to have value ranges, and some of them is going to be undefined, and things like that. So here we have this C3 variable based on this AND operation. C3 is going to have a value between 0 and 15. Similarly, the C_6 is going to be between 3 and 10, the one which we looked at earlier. _7 is going to be between 0 and 7. And using this information and by setting these attributes, we can convert the RTL expansion it's going to look like this one. So basically, we are eliminating the sign extent that happens in the RTL using this value range information by setting that attribute and changing this, the simplified routines that are present in the RTL. So using that one, we can actually generate this simplified code. So now let's look at the challenges we had to face. One of the issues we ran into was in SSA, the value ranges are computed only for the type. And we need the value ranges in promoted modes. So for example, if you have a character and the value range is computed by the value range propagation pass is going to be for the character type. And in ARM, we need it for 4 byte. So we also need, some of the value range based optimizations are based on C language undefined behaviors and things like that. So when an operation wrap is going to simplify that to the type. So if you, I think the best example is the one we ran into with alpha, where the promoted mode was 64-bit, and _34 is a 32-bit register, unsigned variable. So here _343 has the value range shown here. It's a big number. And when you multiply by 2, the operation actually wraps. So value range propagation correctly from the type's perspective says that the value range is going to be between 8 and 86. But if you look at the promoted mode, it's going to have some bits beyond that. So we also needed a wrap attribute.
So you mean that in 64 bits,
Yeah.
shifted
Yeah.
one bit,
Yeah.
it's still
Some values.
but in 32 bits,
It's fine. Yeah. So yeah.
Why do we care about alpha for an ARM optimization?
Oh, it's not. It's a middle-end optimization. It's used by everybody. So, yeah. So because of that one, we had to actually also gather this wrap information during value range propagation pass, and also propagate this information to SSA, and use this as well while we are expanding. So when there is a wrap attribute, we can't actually do this optimization. And other issue is actually, as I told earlier, most of the optimization with respect to value range propagation pass happens within the pass, because there is all the information you need there. And when you try to do it separately, you don't have access to all the information. So that's a challenge. So we also had to, like, sometimes we have a test case and we think that it should be optimized, but when we go and look at the value range data, it's more pessimistic. Now let's look at the other approach. That's doing register promotion in tree level to remove the redundant extensions. Here, the basic idea is that we are going to promote all the computations in tree level to the promoted mode, such that we don't need Subbridge and extensions. I think this is what you probably asked earlier. So here, so if you have operations that's happening in char type, so
end is operate on the word, right?
Sorry?
The logic end is operate on odd. So you have to promote C to D to integer for 32 bits, and for code word for
yeah, that's
why we need to promote mode.
Yeah, that's
but
what
this is doing on the type analysis phase. So we can get the expression type for.
I think like currently GCC doesn't promote the operations to promote mode. It only happens in RTL. That's what we are trying to do.
I think that in Jimpo phase, it's already defined.
No.
Clearly stated.
No. I mean, that's what we want actually, because like if you do that one, we can remove some of the extensions.
Okay, please go on. So
yeah. So like if you look at the example shown on the other side, so here we are actually doing the operation in promoted mode. So that's we are ending in SI mode, and then we are doing the extension to get the 8-bit. So, but if you do this, if you can promote this one to the promoter type, in ARM's case is SI mode, we don't need this one. But obviously it's not as simple as that one, because like when you try to change the operations to the promote mode, you also have to have lots of fix-ups and to preserve the semantics. Otherwise, your program is going to be wrong. So, for example, if you look at the same example like earlier, here what we are doing is actually we are promoting the computations like this addition to the promoted mode. Earlier, the addition was happening in unsigned short, but now we are going to do it in unsigned integer. But the moment we do that one, we also have to do the fix-ups. Like we have to make sure that the value beyond that is actually cleared, and the value we returned is converted again to the value which we need. So using that, we can actually again simplify and get the similar kind of optimized code. So the issues here is actually like we have to make sure that we are inserting fix-ups and conversions to preserve the semantics of the program, and also we have to make sure that the operations that has to be happened in the original mode are preserved. Some of the operations we can't actually promote because they'll run into undefined behaviors and issues like that, especially the shift and the second challenge is actually making sure the subsequent passes optimizes this the promoted modes, actually the computation which happens in the promoted mode, because we are in fact adding some redundancies here, but subsequent passes should optimize them. In conclusion, redundant zero sign extension results in performance and code size penalties. Basically, excessive instruction increase register pressure. Removing redundant zero sign extension is a challenge and has to be approached from multiple levels, partly because of the design decisions GCC has already taken. And patches for the discussed optimizations are currently being reviewed and upstreamed.
So is the implementation of all the optimizations discussed in this presentation done, or are they partly done and some new patches will continue to emerge?
Yeah, for the first part, actually, we did commit to the GCC, but we ran into the alpha issue and we had to revert it, and I am now sending patches again with the wrap information that will go into the, hopefully that will go into the next stage 1. And the second pass, three-level pass, I posted the patch and as a prototype patch some time back, and I got some feedback, and I'm working on them. And I'll be, I'm now in the process of coming up with simple benchmarks, micro benchmarks that can actually show the improvement. And once it's done, I'll do the spec. Once that's also done, I'll be posting it for stage 1 again. Stage 1 again, yeah.
Okay. And once those patches are committed, are there possible further improvement projects to remove even more redundant sign and zero extension elimination, or whether this optimization gets rid of pretty much everything that we can get rid of?
And one of the things actually I looked at when I was making this presentation was that redundant extension elimination, and I noticed that that seems to be very specific to x86, and I'm sure that we can do something there as well. But yeah, no, that's not something which I am.
x86?
Yeah, redundant extension elimination pass in RTL was actually first proposed for x86.
Ah, okay.
And later it was actually enabled for Spark and ARC64. But it's very specifically tuned for x86 architecture, so we probably can do something there.
Yeah, so a generic optimization pass was created without ARM in mind, and we...
no, I think they tested it for x86.
Yeah.
Yeah, and
I don't think ARM64 existed when they wrote it.
yeah, yeah. It was a couple of, 2-3 years back. Or maybe more than that.
Sorry, can I just ask a quick one? So when this started, there was a CRC function that was the motivation for this. Does that now work? Does that now have fewer sign extends? Or zero extensions, I can't remember
yes,
which.
actually, there is an additional AND instruction, which is basically, where we can actually eliminate that one.
Okay.
Yep.
Cool.
RB has CRC instruction.
V8.0 has it as a optional not thing. And anyway, this came up on V7 as well.
Yeah.
So this is not just an RB8 issue.
No, it's a generic issue.
So, do we have any performance data for the patches?
Unfortunately, not. I did benchmark them along the way, but I don't have the numbers for the latest one. The first one I did was actually as part of the VRP. So And that was actually pretty good numbers, but then we took it out. Obviously, we lose some of the value range information. Yeah.
So pretty good numbers in which area?
Yeah. Initially, I was getting something about 1.5 to 2%, like that one.
For speed.
Yeah, for ARM. But the latest one was actually the first approach I'm proposing here is actually watered down version of what we wanted to do, due to some of the issues actually. Like, I mean, initially I was trying to propagate that information in Gimple. So basically, like, I'm setting an attribute in Gimple saying that this extension is, for this Gimple you don't have to do extension. But obviously that increases the memory requirement for the Gimple node, because additional attribute. So Richard Wiener straight away said no.
Which architecture is this optimization more useful for? ARM32, ARC32, or ARC64?
For both.
Equally good for both?
Equally, yeah.
Okay.
So I get a question. Just you propagate the VRP info until the expand pass. So how you have to maintain the passes between the two. So you have to add the Gimple extension to carry the range info, and also the property you carried, the SRP 0 extension and SRP Sign extension. You should use that property and do the expansion. So which target do you use to experiment your idea? And is the GCC community accept such infrastructure change to the Gimple?
Okay. In terms of propagating the value range information to SSA, is already accepted and it's already committed. It's there in the GCC 5.5.0.
Yeah.
But it just said the enabling part, I reverted it now because of the issue we ran into alpha.
So in current GCC trunk, you could not see your patch?
Yeah, because the part which enables is actually reverted, but rest of the infrastructure is there.
Okay,
Yeah.
thank you. Okay.
So do you expect that this will make GCC 6?
Yeah, that's the hope and that's the idea. Okay. Mm-hmm.
Any other questions?
Just a comment, GCC 6 will not be in 10 years. It will be right after GCC 5.
Mm-hmm.
Yes.
They changed the release numbering.
Okay. Thank you very much. This was a very interesting presentation. Thank you, Kugan.